Hello, everyone. Today we're going to look at compound interest. So, last week I had you guys to look at an exponential function. And I wanted to introduce exponential functions to you guys because I wanted to show you how exponential functions are used in real life application. So, the formula that we will look at this week is the continuous compound interest formula. Now, a compound interest is whenever money grows over time. So, your money is going to grow over time either for you or whoever you borrow money from. Okay? So, there are a couple of variables that we need to discuss before we start the formula and applying it. So, the formula that we have is A equals PE raised to the RT. Now, A represents the accumulated value. This is the amount of money that we will gain over an amount of time. P represents the principal. The principal is the amount of money you either borrow or the amount of money that you place into an account. R represents the rate. Your loan or your investment will grow at a certain rate, and T represents the time. So, I guess you're wondering why I didn't mention E. E is one of those numbers like pi. We know that pi is approximately 3.14. Well, E is used for logarithmic functions or exponential functions, whereas we use pi for formulas that involve circles. So, whenever we're mentioning exponential functions or logarithmic functions, we may see the E, and the E is equivalent to 2.71828, so forth. It's one of those irrational numbers. Now, let's use a formula in a real life application. And I'm going to use this name because he's one of my students, and I told him one time at a football game, I was like, baby, you're going to make you some money. So we're going to give some props out to my student Caesar. And Caesar invests $3,000 in a savings account with a fixed annual interest rate of 9% compounded continuously. What will the account balance be after 10 years? So notice I have something underlined, compounded continuously. So, hence the name of the formula we just used is continuous compound interest. So we use that formula to see how much Caesar will gain after 10 years if he invests $3,000. All right, so since we want to know how much he gained, that gain is going to represent A. Use a different color. And we don't know how much yet, so that is what we are looking for. Now, P represents the principal, and the principal is how much money did he put in? Well, he invested $3,000. Remember, E is just a part of the formula. It's kind of like pi. And then we have a rate of 9%. And remember, whenever you have a rate and it's mentioned as a percent, make sure you change it to a decimal by moving the decimal place 2 places to the left and the time. Caesar is going to let that money sit and grow continuously. Continuously means on and on and on and on. He's going to let that money grow on and on and on and on for 10 years. So let's take a look at plugging those numbers in. So A equals 3,000 because that represents P. Remember, E is going to be there. Now, since we're computing, make sure you use the decimal for R. So 0.09 times T, which is 10. All right. So then we get A is approximately, and we plug it in the calculator just like this, 3,000 times E, and that E you'll see around that button ln raised to the 0.09 times 10, and you'll get the amount of $7,378.81. So if Caesar invests $3,000 into a savings account with a fixed interest rate of 9% compounded continuously for 10 years, he will receive $7,378.81. So this is a real life application for an exponential function. The exponential function that we took a look at today is the one for continuous compound interest. Next week we will take a look at regular compound interest. I hope you guys learned something. You guys have a good day. I have a problem attached to this particular example. I want you guys to play around with it. Let me know if you have any questions. Take care.